In this video, we are going to take a look at section 4.4 on solving logarithmic and exponential functions. A lot of these equations we've already done previously in chapter 4, so some of this will be review, but some of these types of equations will be different than what we've seen so far. One type of equation that we have done previously is solving a logarithmic equation where there's only one logarithm. So this case we've already done, right? Solving an equation with just one logarithm in the equation. And you use the loop, meaning you convert the equation to exponential form. And that gets your variable out of the logarithm out into the open where you can solve for that variable. So that'll be like a review. But this is new. Solving logarithmic equations when there's two or more logarithms. And it's really not going to be too much more work than if there's just one logarithm. What we will do if there's two or more logarithms is to rewrite all those logarithms as a single logarithm first. So we will collapse it down to a single logarithm, and then we will convert it to exponential form and solve it just like we are doing for these other equations. All right, so let's take a look at some examples. Excuse me. All right, so here we have log base 2 of x squared plus 7 equals 3. All right, so this is just a single logarithm. We will solve this equation by converting it to exponential form, and I'll follow that loop process in order to do that. So I start with the base of the log, which is 2. That'll be the base of my exponent. I'll raise it to the power of whatever's on the other side of the equal sign. So I'll raise it to the third power, and then I'm going to set that equal to whatever's inside the logarithm. And so I'm going to set that equal to x squared plus 7. All right, and so that's just rewriting that equation in exponential form. And now I can solve this equation for x. What is a little bit different in this section than what we saw previously is that the equation we're now getting is a quadratic equation. We didn't experience that before, but we should know how to handle a quadratic equation, especially this one. All you have to do is get x by itself. So I'm going to deal with this exponent here. 2 to the third power is going to be 8. And then I will get x by itself by first subtracting 7 to the other side. And then I'll get 1. So I get 1 equals x squared. And then to get x by itself, I take the square root of both sides. Now, when I was grading the last set of exams, a lot of my students seem to have forgotten this really important rule that if you take the square root of both sides of your equation, you have to put a plus or minus on that result, right? And so x is equal to plus or minus 1, and that will be our solutions to this equation. So there's two, positive 1 and negative 1. All right, so that's how you solve an equation with just one logarithm. Let's take a look at an equation with two logarithms. So what we will do first here is we cannot do the loop thing. We can't convert this to exponential form while there's still two logarithms here. There's just no way to make that happen. So what we want to do is combine these logarithms together into a single logarithm. This is a skill that we learned in section 4.3 in the previous section. So we're going to add these logarithms together into a single logarithm. So I'll start by writing log. The base will stay the same, so it'll still have a base of 3. I'll take the x plus 12 and the x minus 12 and put them inside the same logarithm. So what do I do with these two things when they go inside of a single logarithm? Because I'm adding here, these will get multiplied together. All right, that was the rule for how logarithms behave. If you're adding two separate logarithms, you can combine those into a single logarithm, but then the things inside of those individual logarithms will get multiplied together inside of that single logarithm. Right? And then because I'm going to have to use parentheses to kind of keep these separate from each other, I'm going to use brackets to hold whatever's inside the logarithm. Again, it's no different than using parentheses. It's just a little bit easier to read and interpret if you use brackets there. And this is still equal to 4. Right? So that's the first step, is to rewrite the two logarithms as a single logarithm. And once we have a single logarithm, it's just like the problem we just did. We're going to convert this to exponential form. We'll start with the base of the log, which is 3. raise it to the power of whatever is over here on the other side, which is 4. So I'm raising it to the 4th power, and then set it equal to whatever's inside the logarithm, which is x plus 12 times x minus 12. All right, and then we're going to solve this equation. So now that we've converted it to exponential form, the x's are no longer stuck inside the logarithm. They're out in the open. We can now solve for these x's, but they are stuck inside these parentheses. So to get them out of the parentheses, we'll have to multiply these together. So we will FOIL. So we're going to get x times x, which is x squared. X times negative 12, that's negative 12x. 12 times x is positive 12x. 12 times negative 12 is negative 144. And then I will also evaluate this exponent. So 3 to the 4th power is going to be 81. I'll combine like terms, and what's going to happen is the 12x's will cancel each other out. And so I will end up with, I'll put it up here, 81 equals x squared minus 144. So it's just like the previous problem we did. It's quadratic, but we can solve this by just getting x by itself. So we will add 144 to the other side, and we are going to get kind of a big number here. We're going to get 225. Sorry, it's a funny looking 5. All right, maybe I should just try that again. All right, 225 equals x squared. We'll take the square root of both sides of this equation to get x by itself. And just like we did on the previous problem, you take the square root of both sides, you have to do plus or minus. And the square root of 225, I just happen to know this one, it's going to be 15. Now, if you go to type this answer in to the homework system, the homework system is going to say, sorry, you actually are not correct. So what is different when you have two separate logarithms, I've never seen this happen with single logarithms, but if your equation starts off with two separate logarithms, it is possible that the answers you're going to get here don't work in the equation that you were given. So these results are definitely solutions to this equation. So it definitely works here, but it doesn't necessarily guarantee that it works in the original equation with the two logarithms that are separate. And while these are mostly equivalent to each other, they're not 100% exactly the same. And we were asked to find the solutions to this equation, not this one right here. So I need to make sure that these two numbers will work in this equation, in the original equation. And so whenever there's two or more logarithms, two or more logs in your original equation, an extra thing you have to do is check your answers. This is not good advice, because checking your answers is always good advice. This is necessary. You have to check to make sure these numbers will work in the original equation. So I'm kind of out of room here. I guess I'll try to squeeze it right here in this space. And so I'm gonna let's check 15 first. I'm gonna check positive 15. So I'm gonna have log base 3 of 15 plus 12 plus log base 3 of 15 minus 12, and that should equal 4. And so when we check this result, we will take 15 plus 12, that's going to be 27. Log base 3 of 27, how many powers of 3 does it take to equal 27? The answer is 3. Here, this is going to be 15 minus 12, which is 3. How many powers of 3 does it take to equal 3? The answer is 1. 3 plus 1 equals 4. And so it works. So 15 is good. So 15 is definitely a solution. Negative 15, however, will not work. And so the problem with negative 15, maybe I'll put that down here. If I plug negative 15 in for x, I'm not even going to write out the whole thing. I'll just stop here. I'm going to plug in negative 15 for x. And so we're going to get negative 15 plus 12. And, you should also plug it in to the rest of the equation. But this will be enough for us to see the issue. Negative 15 plus 12 is negative 3. And this is something we may have briefly talked about previously. Maybe I didn't. If I forgot to mention it, that's kind of an oversight on my part. But this is something you could test on your calculator. you cannot take the logarithm of a negative number. It's undefined. It's like dividing by 0. And so this is undefined, which means it doesn't actually work in the equation, which means negative 15 is not a solution to that equation. It breaks this equation. And so we have to throw that one out. So make sure that whatever answers you're getting do not cause negative numbers to show up inside of your individual logarithms, because if it does, it is not a solution. It makes the logarithm undefined. It works here because this would come out negative 3. This would come out as negative 27. And when you multiply negative times a negative, you get positive 81. So negative 15 actually works for this equation, but that's not the one we were trying to solve. We were trying to solve this one. And with the x plus 12 and the x minus 12 in separate logarithms, negative 15 does not work. All right, so just 15 is the only answer you should type in to the homework system. All right. Let's talk about exponential equations. So again, there will be some here that we have done previously and some that will be new. The methods you want to use to solve an exponential equation is to either get both sides to have the same base. You should try that technique first because that is always a lot easier than the alternative. So try to see if you can make both sides have the same base. If so, you just set the exponents equal to each other and you can solve that way. Again, I kind of messed up on my numbering here. This should be technique number 3. And we want to use technique number 3 because for the problems in this section, we want to be able to approximate our answers to 4 decimal places. So we want to make sure we solve it in such a way that we are able to plug it into our calculator. And technique number 3 allows you to do that. And that technique is the technique we just learned in section 4.3. We apply a log base 10 to both sides of the equation. And then that allows us to bring our exponent from up in the air, multiply it down in front of the logarithm. And once it's down on the ground, we can solve for x from there, right? And then whatever we get after we solve it for x, we can plug into our calculator because log base 10 should work in everybody's calculator. All right, so let's go ahead and give one of these problems a try. So here we have 2 to the x minus 4 power equals 7. So the first thing I should try to do is to rewrite both sides so that they have the same base. Explore that option first. However, with 7, we're not going to be able to write that as 2 to some power. That's not going to work out. So technique number 1 doesn't work here. So we'll have to use the other technique, which is apply a logarithm to both sides of the equation. So I will apply a log base 10 to the left-hand side and a log base 10 to the right-hand side. All right, so like this. And the benefit of this is it allows me to take this exponent here in the logarithm on the left-hand side and bring it down in front of the logarithm. That is a rule that we learned in section 4.3 for how logarithms behave. It's a really handy rule. I mentioned it was my favorite rule about logarithms. So you bring the exponent, multiply it down in front. Because there's 2 terms here, x and 4, we will need to use parentheses when we multiply it down in front of this logarithm. So put the x minus 4 in parentheses, and then we're going to have log base 10 of 2 left. So the 2 is going to be left behind in this logarithm, but the exponent gets to make it out. On the right-hand side, we're going to have log base 10 of 7. So this is a method that we explored in section 4.3, but the examples we looked at weren't quite this complicated. And so you have 2 choices here. You could distribute the logarithm into the parentheses, or you could divide this logarithm to the other side. And I think it keeps things a little bit more manageable, a little bit easier, a little more clean if you divide the logarithm to the other side. So you could distribute it, but then you're going to have more logarithms to deal with because you'll have, a copy of it will go to each term. So instead, let's just divide this log base 10 of 2 to the right-hand side of the equation. Excuse me, I'm drinking some seltzer water. It's carbonated, and I feel like I'm having some indigestion because of it, and I just ate lunch too. So I'm sorry I keep pausing. I know it probably looks funny, but I just had lunch and a bubbly drink. So, all right, so the logs here are going to cancel out, and we'll have the x minus 4 remaining. Because the logarithm goes away, we don't need the parentheses anymore around the x minus 4. And on the right-hand side, we're going to have log base 10 of 7 divided by log base 10 of 2. We talked about this in section 4.3. You might be tempted at this point because, logarithms, again, are unfamiliar. You might not be very comfortable working with these logarithms, but you do not want to plug this into your calculator yet. You want to finish solving the equation in an exact a manner as possible. And then at the end, after you've solved it for x, then you dump the whole thing into your calculator to get your approximate answer. Right? So don't plug this in. We don't want decimal numbers here yet. Let's just wait, get x by itself first. We're almost there. So now to get x by itself, we will add 4 to the other side. Right? And that's going to cancel out the minus 4. I'll go ahead and continue up here. So we're going to get x equals, it's going to be kind of messy looking for a second. We'll get log base 10 of 7 over log base 10 of 2, and then we'll put the plus 4 to the side of that fraction. And so this is the solution to the equation. This is the exact solution. So if it asked for an exact solution, then this would be okay. This is what you would want. You want to leave it in logarithmic form. And while the screen, I guess I cut off the directions, but I'm 100% certain on our homework system, it's going to ask for an approximate solution. And so we want to plug this into our calculator, and it always asks to round to 4 decimal places. And so let me pull up the calculator. All right, and plug this into our calculator. Now remember, my calculator works backwards than most calculators probably would work, where I have to type in the number first and then hit logarithm, instead of typing in log first and then typing in the number. So I'm going to have to hit 7 first, and then log of that. So that gives me log base 10 of 7, divided by, to do log base 10 of 2, I'm going to do 2 first, log of that, and then I'm going to go ahead and hit, I don't know, let's see what happens. I'll see if this answer makes sense or not. I'm going to hit plus because I want to go ahead and add the 4. I kind of was thinking maybe I should just do that separately, but let's see if I can just kind of put all the calculations in at once. So I'll hit plus. It went ahead and resolved that calculation. So notice the number changed. So it went ahead and did that division, but now I'm going to add 4 to that and hit enter. And so I'm doing this calculation here, which is what I have as my solution. And this is the approximate answer I get. We want to round it to 4 decimal places. So I look at the 5th decimal place. Okay, I'm having trouble just highlighting that number. And it's a 5, which tells me to round up. So this 3 is going to round up to a 4. So 68074. See if I can remember that. 68074. And then the decimal place goes right there. And so this is what you would type into our homework system. All right, so that's an equation with one exponential expression. Notice it says that in the directions up here. So because it makes a big deal of that description, you probably can guess what the next type of problem is going to be. It's going to be an equation involving more than one. So here we have 2 exponential expressions. Right? I was going to say 2 exponents, but really I should be more precise. So 2 exponential expressions here equal to each other. In my opinion, this is one of the most difficult problems to do in chapter 4 for that matter, but in section 4.4. It's tough. But with practice, it's manageable, right? So we cannot, even though it looks tempting here to think, oh, maybe these could have the same base, because 21 is associated with 7, right? 7 times 3. But there's no way to write 21 as 7 to some power, right? 7 squared is going to be 49. So there's just no way to get 21 using exponents. I think I said that the right way. There's no way to get 21 using 7 raised to a power, right? At least not an easy way to do that. So we're going to be stuck using the other method here. So we have 21 to the x power on the left-hand side. We have 7 to the x plus 3 power on the right-hand side. And even though there's 2 exponential expressions here, this other method still works. We will apply a log base 10 to both sides of the equation. Right? And so in both cases, what that's going to allow me to do on both sides of the equation is to take the exponent from inside the logarithm, multiply it down in front of the logarithm. I can do that for both of these, right? So that's a nice, useful property of logarithms that is going to help us out here. So this x goes down in front of this log, so I'm going to get x times log base 10 of 21. Just like in the previous problem, because there's two terms here, when I write the x plus 3 down in front, I'll need to put it in parentheses, and then I'll have log base 10 of 7. All right. Here, in the previous problem, we had this similar situation, and we opted to divide the log to the other side instead of distributing it. That option is not as good of a choice here. You could divide this logarithm over here, but then you're still going to have x with this logarithm, and you're going to make that worse. You're going to make it a fraction with two logarithms attached to that x, and that's just going to be tough to manage, I think, and maybe a little scarier because it's going to be a fraction. We can avoid that fraction by distributing the logarithm in this case. So for this situation, I would recommend distributing the logarithm into the parentheses rather than dividing it over here and having to deal with that fraction. All right, so here I'll have x log base 10 of 21. On the right-hand side, this will become x log base 10 of 7 plus 3 times log base 10 of 7. And it might look kind of strange to keep the logarithm behind the x, but that's just the standard way of dealing with logarithms. You don't want to put it in front of the x because then it's confusing whether x is inside the logarithm or outside the logarithm. By having x in front of the logarithm, there's no confusion. It's clearly outside of the logarithm, right? So now to solve this for x, I'll need to get both of my x's on the same side of the equation. So I'm going to take this term here and subtract it to the other side. Right? I'm going to subtract because we're adding here. So I'm going to subtract it to the other side. So I'm going to subtract x log base 10 of 7 over to the left-hand side. And I think I can maybe squeeze one more line down here. Let me use a different color though so it stands out a little better. So I'll have x log base 10 of 21 minus x log base 10 of 7 equals, so these get canceled out. And so this is what we're going to have left over on the right-hand side. We'll have 3 log base 10 of 7. Right. Now, there's a couple more steps to go, but maybe this is maybe the most crucial step that you need to know, which is you still have two x's here. To shrink this down to 1x, you have to know to factor it out. Excuse me, my voice kind of cut out there. So we want to factor out the x, or undistribute it. So it's a common factor in both of these terms. Let's factor it out as a common factor. So I'm going to continue way up here. Hopefully I'll have enough room. We're factoring out the x, and then in parentheses, what's left over when you take the x away from both of these? You'll have log base 10 of 21 minus log base 10 of 7 in parentheses, and then the right-hand side is still the same, 3 log base 10 of 7. Okay, now you could go ahead and just finish out this problem by getting x by itself by dividing this parentheses to the other side. But it's a fairly complicated looking answer, and typing it into your calculator could be challenging. So to make the answer look a little more friendly, to make it easier to type into your calculator, there's one more step you can take, which is to combine these two logarithms together into a single logarithm. So again, this is something we practiced in the previous section. So because we're subtracting here, when I go to write this as a single logarithm, I'll write log, one logarithm. I will divide these when I put them inside of a single logarithm. So I'm going to take the 21 and the 7, and they will get divided when I put them inside of a single logarithm, which is going to give me log base 10 of 3. So that kind of gives away why they made these numbers so compatible with each other over here, so that when you got to this step, they would divide nicely, right? And so I'm going to have x log base 10 of 3 equals 3 log base 10 of 7. And now we can finish out this problem by dividing this log base 10 of 3 to the right-hand side of the equation. that cancels out. And so we're going to get x. I'm going to try to squeeze it right here. X equals, and here's where I'll get my approximate solution. So again, this is the exact solution still, but I'm going to type that into my calculator to get the approximate solution. So let me pull up my calculator again. All right, and I'm going to clear this out, and I'm going to take 3 times, again, I have to type it in backwards, 7 log, and then I will divide that by log base 10 of 3. All right, so now, I really probably should take a little more care here. Whenever you have more than one thing in the numerator or the denominator, when you type it into a calculator like this and you're putting it all on one line, it's probably a good idea to put those things in parentheses. So put the numerator in its own parentheses, put the denominator in its own parentheses. But order of operation, I think we're still going to be okay. We're going to be safe with the way we type this in. And so we'll hit enter, and we get this. So again, rounding to 4 points, look at the 5th decimal place, which is a 3, and which means I'll round it down, which means this will just stay. I don't know why I'm having trouble doing this today. This will just stay as a 7. So 53137. Let's see if I can remember that. 53137 decimal place right there. And so this would be our approximate solution, which is what they're going to be asking for. All right, let's take a look at this example. So one more example. This one also has 2 exponential expressions. You could solve this equation in the same manner that we just did the previous problem, using logarithms, bring the exponents down. You saw all the work that was involved there. But this one, we can use our shortcut. We actually can rewrite both of these to have the same base. So I just wanted to illustrate how much of a time saver it is if this option is available. And so here, the 9, let me try to draw that circle again. The 9 can be written as 3 squared. So I can rewrite the 9 with the base of 3. And so now it matches the base on the right-hand side of the equation. So what's going to happen, this part's a little tricky. You replace the 9 with 3 squared, but then we have to bring this exponent down with that, right? Because that 3x is still applying to this 9 right here. And the right-hand side hasn't changed yet. And what do you do here when you have one base with 2 exponents? You multiply those exponents together. So this will be 3 to the 6x power equals 3 to the x plus 3 power. And so now we have 2 exponents that are equal to each other with the same base. So the shortcut here is the only way this equation can be true is for this exponent to equal this exponent. So 6x would have to equal x plus 3. And I can just avoid using logarithms. Even though technically logarithms would make this possible, right? If I did log base 3 to both sides, it cancels out the base 3 exponent and I get this result. But we don't even have to think about it that way. We get both sides to have the same base, then we just set the exponents equal to each other and we're on our way. So now we'll solve this for x. We'll subtract x from both sides. We'll get 5x is equal to 3, divide by 5 on both sides, and we get x is equal to 3/5. Let me write that again. Now, if it makes you type it in as a decimal, you could type this into your calculator, and you would get just 0.6. Right? So I'm not sure which way it might want the answer. Maybe it would accept it as a fraction, or maybe it wants it as a decimal, but either way, it's a nice answer either way. Okay. All right, now at the end of this section, there are some word problems. These are going to be, especially the exponential ones, are going to be kind of challenging. So let's take a look at a couple of these. And then we have one logarithmic word problem I was going to take a look at. The logarithm ones are not nearly as difficult because they kind of just give you the equation. You just got to plug the numbers in and solve. But the exponential ones, there's a little bit more going on. So let's take a look at this problem. Prehistoric cave paintings were discovered in a cave in France. The paint contained 37% of the original carbon-14. The half-life of carbon-14 is 5,730 years. Estimate the age of the paintings. So the formula that you want to use to do this problem is not actually on the screen here, but it's this formula here. A equals a sub 0 e to the RT. And if that looks a little bit familiar, I hope it does, because we actually did see a formula very similar to this in section 4.1. It was a while ago, but it was this formula. It was the formula for compound interest. A equals P e to the RT. Except instead of P, we're using a sub 0 here, right? But otherwise, it's really the same formula. And so this formula is for radioactive decay. So I am a math teacher. I'm not a biology teacher. I'm not a nuclear physicist or anything like that. But my rudimentary understanding of how radioactive decay works, especially when it comes to like dating objects like this, carbon-14 is only produced in living things. So plants, animals, our biological processes generate that carbon-14. But carbon-14 isn't stable, right? The half-life of carbon-14 is 5,730 years. So what happens is, over time, some of that carbon-14 is going to break down. I don't know what it breaks down into, if it's another form of carbon, like maybe it breaks down to carbon-12 and some other byproduct, but it breaks down. And so you can measure the byproducts of that breakdown in an object like this paint. Now paint, you might say, what does paint have to do with this? It's a chemical. But probably with these cave paintings in prehistoric times, you know, I wouldn't say probably, definitely, the paint was made with plants, right? So it was made from living material. And so that carbon-14, once the thing stops living, once the plant is killed to make the paint, it stops producing carbon-14 at that point. And then over time, that carbon-14 breaks down into its byproducts. And so when these cave paintings were discovered, they measure those byproducts in the cave painting to figure out how much decay occurred and how much is there currently. So you look at how much carbon-14 you have currently today and how much of the byproduct you have today, and you can work out this ratio of how much you lost, right? In this case, we lost 63%, right? 37% of the original carbon-14 remains. We've lost the rest of it based on the byproducts versus the ratio of, the ratio of the byproducts with the ratio of the carbon-14, right? So that's, because that was a part of it I never understood is, well, how do they have an idea of how much is there from the original amount? So it's based on measuring the byproducts from the decay, right? The half-life of carbon-14 is how long, on average, it's not an exact measurement, but on average, how long does it take for you to lose half of the carbon-14 that you started with? It takes, on average, 5,730 years. And that's regardless of how much you start with. So if you have 10 grams, it takes 5,730 years for that to decay down to about 5 grams. If you had 1,000 grams, it would still take 5,730 years for that to decay down to 500, right? So whether you're going from 10 to 5 or 1,000 to 500, it takes the same amount of time. That's how half-life works, and that's how these exponential decays work. All right, so that's my rudimentary understanding. I'm sure if you wanted to look into it, you probably could find better sources than me for understanding that a little bit better. This formula, so here we're being asked for the final amount of carbon-14, the initial amount of carbon-14, R is the decay rate, which we also are not given, and T is the time, how much time has passed. We are not told these amounts. We don't know how many grams of carbon-14 we're starting with. We don't know how many grams of carbon-14 we're ending with. What we do have is a ratio. We have a percent. So if you're given that information, the amount remaining of carbon-14 as a percent, there's an easier way to set up this formula. And that is to take the a sub 0 and divide that to the other side. And so we get a over a sub 0 equals, and I know it makes a fraction, nobody likes fractions, but what's nice about this fraction is this a divided by a sub 0 is the percent remaining, right? So you're taking a ratio there of the amount that you have left divided by the amount you started with, and that's going to give you the percent that you have left over. which is this 37%. So this is kind of an unusual maneuver. We don't normally get this opportunity, but we actually get to replace two variables at once with this one number, right? So this 37% is my a divided by a sub 0. I replace that fraction with 37%, which I need to write in decimal form. So 37% is 0.37. All right, equals e to the, now I have two variables here. I'm being asked to estimate the age of the paintings, which means I'm looking for the time, but I don't have R either. So I actually have two unknowns here still to deal with. I'm not going to be able to find the time until I actually have a value for R. So we actually are kind of stuck working through the rest of this problem at this point. We need to figure out what R is equal to first. Once we have R, we can plug that in here. Then we can solve for t and find out the time it would take. I'm going to leave some space for the work that is left to do on this problem, but we have to take a timeout. We're going to have to pause what we're doing here and do a little bit of research, calculation, whatever you want to call it, to find R. And the way you find R, I hope I left myself enough room there, is to use the half-life. That's why they're giving us the half-life. You might have been tempted to take that time and plug it in here, but again, time is what we're looking for. This time is to help us find R. So we're going to use this to find R, so I'm going to do that here. So we have to start over again with this same formula. A divided by a sub 0 equals e to the RT. And for half-life, what percent will we have remaining? We will have 50%, right? That's what half-life means. It's the amount of time for half of your carbon-14 to decay, which means you'll have half remaining. You'll have 50% left over. And so for half-life, my ratio is going to be 50% equals e to the R. I don't know R. That's actually what I'm going to be looking for here. But for half-life, I know the time. It takes 5,730 years. So I'll plug that in for t. So it was a time, but it's not the time for 37%. It's the time for 50%. And so here's where I will plug that in for time. And now I can solve this equation for R. It's an exponential equation. And so we will use logarithms to bring the exponent down to the ground. Now in the previous problems when we were solving exponential equations, we used log base 10, which you could still do here, but it's going to be a lot easier using natural log because natural log is log base e. So natural log, the base of that log, matches the base of this exponent, and it's going to make things work a lot more smoothly. And so instead of doing log base 10 to both sides, this time I will choose to do natural log to both sides of this equation. So I'll do natural log of 0.50 on the left-hand side, natural log of e to the R times 5,730 to the right-hand side. I wasn't sure what was going to happen with my webcam here. I don't know if when I export the video if it's going to work this way, but it's a little bit transparent so you can still see what I'm writing underneath it, which is pretty cool. I didn't know it would do that. All right, so the benefit of using natural log here, which again is log base e, is that the base of the logarithm matches the base of the exponent, so they actually will just cancel each other out. That logarithm just goes away, and so we don't even have to use the power rule to bring the exponent down to the ground because the exponent just disappears. We're just going to get R times 5,730 here, right? And on the left-hand side, we'll still have natural log of 0.50. And now I can solve this for R by dividing 5,730 to the other side of the equation. Now, sometimes students, like if you look this up online and you look up formula for decay rate, you'll actually see this as the formula. It's natural log of 1/2 or 0.5 divided by the half-life. Right? But we were able to actually derive that ourselves from this formula instead of having to memorize a whole separate formula to do this calculation. Right? So now I plug this into my calculator and we're going to get a pretty unpleasant number. So let's just see what we get. All right. So we're going to clear this out. And again, I have to do it backwards. So I have to do 0.50 first, then natural log of that, right, which is going to give me negative 0.6, whatever. But then I have to divide that by a pretty big number, 5,730. And so I get this result, right? And so notice, and this is pretty common, most calculators will do this. If you're not paying attention to the end of that number, you're going to think, okay, r is equal to negative 1.2096 or 97, right? But that's not all there is to that number. This one has a lot of decimal places. Your calculator probably won't have quite this many, but at the end of the digits, your calculator should also be displaying this or something similar to this, e negative 4. That's a really important detail to this result. If you don't catch that, you will not have the right value for r. You will not get the right answer from this point. So it's negative 1.2097 times 10 to the negative 4. So if you ever see this e function in your answer, that means you have scientific notation in your answer. And it means it's times 10 to this power. And so let me see if I can remember this. So it'll be negative, and that makes sense that it's negative because it's a decay. You're losing carbon-14. So it's negative 1.209, came after 97. Okay, that's what I thought it was, but I wasn't 100% sure. 97, okay, times 10 to the negative 4. Now, the other difficult thing about that is this is the value for r. This is what we now need to use here and plug it into this formula here. But it's a tough number to type into your calculator because it's scientific notation. So you could also write this number as negative point. You move the decimal place 4 times. Because it's negative, you want to move it to the left to make the number smaller. So moving the decimal 4 times to the left, we get 0.000120097. And there's more to it than that, but this will be another way that you could write that value for r. All right, and that's easier to type into your calculator. While I'm rounding it off on the screen, because I don't want to write 100 decimal places for it, when you go to do this calculation, you don't really want to round that number off. Even though my answer is going to be rounded to the nearest whole number, you want to keep these numbers as precise as possible until the very end of the problem. So on paper, I'm rounding it off, negative 1.2097 times 10 to the negative 4 t, right? So the t gets copied down. But when I go to do the calculation in my calculator, I'm going to actually keep as many decimal places as I can possibly keep. That number is still in my calculator, so don't clear it out, keep it there, and then when you need to use it again, you'll have all the decimal places ready to go. So now I want to solve this equation for t to find the time. So it's a mirror situation to what we just did over here. It's the same, we're in the same boat. I'm trying to solve for t that's stuck in this exponent. I'm going to use logarithms to do that. Because it's base e, I will use a natural log. It'll work out better that way. So I'm going to do natural log of 0.37 on the left-hand side. Natural log of e to the negative 1.2097 times 10 to the negative 4t on the right-hand side. The natural log cancels out the e, right, because they have the same base. And so I'll end up with natural log of 0.37 equals negative 1.2097 times 10 to the negative 4t. And now I can solve that for t by dividing this to the other side. So I'm out of room on my screen, but I'm going to write what it looks like up here. So we take the natural log of 0.37 divided by negative 1.2097 times 10 to the negative 4, right? And that's going to give me my time. And I probably should switch colors there. So let's type that into our calculator. Okay, so I want to use all these decimal places here. So I guess I can kind of cheat, and you're going to be able to cheat also. But I think I can just copy and paste. So that's what I'm going to do, is I'm going to highlight all these digits and copy them, because I'm going to lose them here in just a second. The way you can cheat on your calculator is your calculator should have a previous answer button. So you can go ahead and type in this logarithm first. It's going to clear out the answer you just had, or it's going to move to the next line or whatever. It's not going to clear it out, or maybe it depends on what kind of calculator you have. But either way, type in the logarithm, and then hit divide by, and then use your previous answer key on your calculator to use the previous answer, which will have all the decimal places so that you're not rounding off. All right, so I'm going to do natural log. I guess I'll move it over here. So I copied and pasted it, hopefully. Natural log. Whoops, I did the wrong thing. Okay. Now it said invalid input because it did natural log of the negative number. I forgot, even though I've said it multiple times on this video, I have to type in the 0.37 first, and then natural log of that. And then I will divide by the answer I copy and pasted. Let me see if this is going to work. Oh, no, it's not letting me do it, actually. No, it didn't like that. It said invalid input. Okay, I guess I can't. So here's what I'm going to do instead, is I'm going to do natural log of 0.37 first, to get the exact answer that you're supposed to get, divided by, so here's another trick I see students use on the test. Instead of performing this calculation and getting the decimal, they'll just leave it as a logarithm, keep it exact, and then they'll use that here instead, and then that way they don't have to worry about rounding off a long decimal number, right? So I'm going to divide by, I need to use parentheses here if I'm going to do this, because I need to keep all this in my denominator. Divide by the way we got this number, which is natural log, natural log of 0.50, so I have to do the 0.50 first, divided by 5,730 years. All right, so I'll close the parentheses on that. And so this will give me the same number, right? It's how I got this number to begin with. And then we're going to take natural log of 0.37 divided by that number, and I put that in parentheses to make sure. And notice, so you can actually see it here, right? When I type that in, I got that same number back that I had on my screen. So now I will hit enter to actually carry out the full calculation, and this is what you should come up with. 8,219.128. We want to round this to the nearest integer, which means the nearest whole number. So we're going to round it to this not decimal place, but this place value. So we look at the first decimal place to decide, do I round that up or do I round it down? Since it's a 1, I round it down and I'm going to keep it a 9. So 8219 is going to be my final answer. So 8219 years. So that would be our estimate for how old the cave paintings are based on the ratio of carbon-14 to its byproducts from the decay process. All right, so sorry that took some time, a little bit longer than I thought it would. It looks like I have a couple more examples here of exponential word problems. The video is already hitting the 50-minute mark. I was doing so good on time before. I was like at 30 minutes, and I just spent like 20 minutes on one problem. So I apologize for that. I'm actually going to skip this one, so I hate to do that, but it's another carbon-14 problem. But this time they actually give you the amounts. So instead of doing a percent, you will plug in, I'll just go ahead and tell you how to kind of set it up. 3.9 is the initial amount you're starting with. So that gets plugged in for a sub 0. That's a common mistake students will make. They'll plug that in for a on the left-hand side of the formula, but this is actually the initial amount. It gets plugged in for a sub 0 on the right-hand side of the formula. Decays down to 1.7 grams. That's the final amount. And then you can use the same R from the previous problem. Because for carbon-14, it's the same half-life. The decay rate's not going to change. So this problem really wouldn't have taken too long from the previous problem. Right, use the R from the previous problem because it's the same half-life. You'll get the same value for R. So you can just jump right into plugging everything into your formula and solving it. Maybe I should just go ahead and do it. I don't know. I'm already like halfway there, I feel like. So we'll use this formula. Right. We have the initial amount, which is 3.9. And remember, in math, anytime you see a subscript of 0, that usually means the initial amount of something, the starting amount. And so that's going to be 3.9. The final amount is 1.7. We'll have e to the r, which is the negative 1.2097 times 10 to the negative 4. I don't have to recalculate it. And this goes for your homework as well. So on your homework, anytime it has carbon-14, you don't have to recalculate this value for r. You calculate it once and you can just use it over and over as long as it's carbon-14. Now, if they change to a different element, then the half-life will be different. The value for r is going to be different. You'll have to recalculate it. and then t, right? Because that's what we're trying to find out, is how long will this take to go from 3.9 to 1.7. Now, so you just dump those numbers into your formula, and then you want to solve this for t. What is different about this situation, so this is kind of why I changed my mind, even though this is going to come up on the next problem we're about to do. To solve this for t, you want to use natural log like we did on the last problem, but you can't do that yet. While there's a number in front of e, the logarithm is not going to cancel out that e. It's not going to bring the exponent down to the ground if there's a number in front of that exponent. And so you have to clear that out first. And so we'll get rid of the 3.9 first by dividing it to the other side, right? It's being multiplied to the e, so to cancel it out, we will divide by it on both sides. And so I'm going to end up with an unpleasant fraction, 1.7 over 3.9 equals e to the negative 1.2097 times 10 to the negative 4t. Now I will use natural log. So before you can use a logarithm on an exponent, you have to get the exponent by itself first. If there's something in front of it, it's going to get in the way and the logarithm's not going to be able to do its job, right? Now I will do natural log on the right-hand side, natural log on the left-hand side. The natural log cancels out the e because they have the same base. So I get negative 1.2097 times 10 to the negative 4t on the ground. On the left-hand side, I'll have natural log of 1.7 over 3.9. And now I will solve this for t. I'm in the same boat I was on the last problem. We're going to divide by this negative 1.2097 times 10 to the negative 4 on both sides. Negative 1.2 times 10. It's a little bit messy, but you get the idea, hopefully. And so this is what I want to type into my calculator. Natural log of 1.7 over 3.9 divided by that value for r equals t, right? Because it's going to cancel out over here, and I'll just have t by itself. So that's what I type into my calculator to get my value for time. This one's being a little ridiculous in how precise it wants the answer, because with radioactive decay, it's never a precise value. I mean, it's always an estimate, right? So it's in the ballpark of this time frame. So to round it to 2 decimal places, so nearest hundredth means 2 decimal places. It's misleading because the calculations, the conclusion, maybe is a better way to put it. The conclusion we're drawing from this problem is not that precise. And so by having 2 decimal places, you're misleading people into thinking you have this very precise amount of time for this, thing that you're dating, when it's really not that precise to that many decimal places. Really, we should go the other way. We should be rounding to like the nearest hundreds. That's a better indicator of how precise the calculation is, right? The conclusion puts it in the ballpark of that time frame, but it's not exact, right? And so you would type this into your calculator. Again, to avoid rounding that number off, you should use natural log of 0.50 divided by 5,730 to get all the decimal places back in place of this, right? So don't use the rounded off number. Use either all the decimal places that your calculator provided, or go back and redo that calculation to get all the decimal places back, so that you're doing a precise calculation, because it needs to be pretty precise to get this right to 2 decimal places. So I'm going to go ahead and leave it at that. This problem is a different scenario, but if you look at the formula, it's the same formula. It's just the letters are a little bit different. A person bought a car for $21,007. After 3 years, the car was worth $11,958. Assume that the price is decreasing according to the continuous exponential decay model, P equals P sub 0 e to the RT. Find the depreciation rate, it's just like the decay rate, to the nearest 1/10 of a percent. Now this one's also misleading, because for part A, you're going to round off that percent. But for part B, you should not use that rounded number to do your next calculation. You want to keep all the decimal places when you go to do the next calculation, right? And then find the value of the car after 5 years and round that to the nearest $100. That's a more realistic way of interpreting the result, right? It's in the neighborhood of this value. So this is actually a pretty good way of modeling the value of a car, as is common wisdom. When you drive a car off the lot, the value just drops immediately, right? So when you buy a new car, the moment you drive it off the lot, the value drops right away, like this. And then it kind of, slowly loses value over time. This is an exponential function, right? This is the graph of what an exponential function looks like. That's why this formula is a good way to model it. All right, so for part A, we want to find the rate. We want to find R. So we will use this formula. We'll plug in the numbers that they give us. So again, don't get this backwards. The initial value of the car was $21,007. That's P sub 0, right? That's the initial amount, which goes here. It doesn't get plugged in on the left-hand side. For some reason, students want to put the big number on the left-hand side, the small number on the right-hand side. And for decay, for depreciation, whenever it's going down, it's the opposite. The big number goes on the right-hand side. The small number is the one that goes on the left-hand side, right? So after 3 years, that's the time, the car is worth this amount. And so that's the final amount that the car is worth, right? It's lost value over time. And so the final value is $11,958. The initial value, that's the 0, right? The P sub 0 is the initial value. The starting value is $21,007. E to the R, we don't know R, that's what we're trying to calculate. And then the time for it to go from the 21,000 to the 11,000 figure is 3 years. So you're going to plug in 3 for the time. So this is just like the problem that we were just looking at on the previous screen, right? I want to solve this for R. It's stuck in the exponent. I will use a logarithm to make that happen. But before a logarithm will be effective here, I have to get rid of this number, right? This number is going to get in the way of the logarithm doing its job. So I will have to divide the $21,007 to the other side of the equation. So that gets rid of that. We'll get $11,958 divided by $21,007. Sorry, it's going all crazy there. Equals e to the r times 3. You could write that as 3r if you want, but I'll just leave it like that. Now a logarithm will get its, how do I want to say this? It will be effective is what I was going to say the first time. I always, mess up on my words because I think of saying it one way, then I change my mind as I'm saying it, But logarithm will now be able to do its job. It will be effective since that number is not in the way. So I'll now apply a natural log to the right-hand side of the equation, which means I need to do the same thing to the left-hand side. The natural log cancels out the e because they have the same base. And so I will end up with natural log of 11,958 over $21,007 equals r times 3. And so this one's fairly easy to solve at this point. We just divide by 3 on both sides to get r by itself. Right. So now if you're memorizing the way to find r as natural log of 0.5 divided by the half-life, that works for radioactive decay if you have half-life. But that doesn't work for this kind of problem. So to find r in this situation, you just have to know how to go through the process. So you really should make sure you know how to do that. All right, and so we get r here, and need a calculator. Let's move this over here. So I'm going to do this part first. So the 11,958 divided by 21,007. I will take the, I guess maybe I should enter on that first. I will take the natural log of that number and then divide that by 3. Whoops. Whoops. What did I do? Okay, go back. Okay, 3. All right. And so we get this. And that looks about what it should. So it's negative, again, because we're losing value. The rate's going to be negative. And we wanted to round this. This one, again, this one's kind of tricky. For part A, round it to the nearest tenth of a percent. Now, if you think round this to the nearest tenth, you'd be rounding here. And the 8's going to make you round that up to a 2. And you'll have 0.2. But that's not a percent. So if we convert this to a percent first, this is going to be 18.7818%. So the way you make it a percent is you move the decimal to the right twice. So this is 18%. Then from there, we want to round that to the nearest tenth. So we're going to actually round it to this value here. And so because this is an 8, this 7 is going to get rounded up. And so it's going to be negative 18.8% is the answer that I want to type in here. So my initial, I guess let's start with the initial thing here. We got negative 0.1878 ... lots of more numbers. We convert that to a percent, and so it's going to be negative 18.78 ... percent is the value for r. And then now we're going to round that to the nearest tenth. So it's going to be negative 18.8% is the approximate value for r. That's what you want to type into this box here. And that includes the negative sign. You want to make sure it's a negative percent. So make sure you type in the negative sign with that. I believe you should type in the negative sign. If you might double check me on that by viewing an example. All right, so that's part A. I didn't leave myself much room for part B. So I think what I'll do, I haven't really used this yet, but let's use the eraser and let's erase this so that I have room to do part B. All right. And so I'm going to do part B here. Whoops. Okay. Let's try that again. Okay, so this will be part B. We shouldn't need as much room to do part B. Find the value of the car. That's P, right? The final value of the car after 5 years. So now the time is going to be 5. And we also have R. So you can actually use either of these two numbers, but the one that makes sense is to start with the initial value, P sub 0, as your initial value for part B. So we don't know the final value. That's what we're trying to find. The initial value is the $21,007. That's how much we bought it for. $21,007 times e to the power of the negative 18.8% times the time, which is 5. Sorry, I'm confusing myself with the last problem we did, where we didn't know the time. Let's try that 5 one more time. Okay, times 5. So we're going to multiply these together. All right. Whoops. Okay, I really messed up there. I moved my screen. Sorry. I don't know how that's going to look on the recording, but let's see if it'll let me move it back. Okay. Sorry about that. I accidentally grabbed the border of my recording area and moved the recording area. So I'm sorry if that was a little bit discombobulating. All right. So this is what I want to type into my calculator. But remember, for this number, we don't want to use the rounded off version of it. It's really misleading for part A that they make you round it to 1 decimal place. And then for part B, if you use that rounded number that you got from part A, you will get the wrong answer for part B. You have to go back to the unrounded number. And also, you don't want it as a percent. That's another misleading thing. For part A, we're thinking of it as a percent for our answer. But in the formula, we don't want to type it in as a percent. We want to type it in as a decimal number. So we're going to go back to using the decimal form of the number, not the percent form, but the decimal form, and the unrounded version of that number. So go back to using all the decimal places. So, which I still have in my calculator. So this time I think I can actually take advantage of that. So let me go back to my calculator. Whoops. Hopefully it's still there. Okay. And so here's that number, unrounded. I want to multiply it by the time, which is 5. So I'm going to have to multiply these together first. So I'll take this result I just got, multiply it by 5. All right, and it gives me this. Now I want to take e raised to that power. So again, my calculator is a little bit backwards. I have to have this number first, and then I hit the e button, which I don't actually see on here. Okay, this might be a problem. I might not. Oh, it's right here. Okay. Usually you'll see the natural log with the e close together because they really, like here, the base 10 exponent with the base 10 logarithm. They kind of put those close together, but they didn't do that with e for some reason. But that's right here. So I'm going to take e raised to that power. So I think when I hit this button, it'll automatically do that. No, it didn't. Okay, so that's just the value for e. Okay, this is, I might have just lost the number I just had. Okay, I didn't expect it to work that way. I'm sorry. So let me start back over. Oh, this stinks. Okay. So going back to getting this number, it's 11958 divided by 21007. We'll take the natural log of that and then divide that by 3. That gets me back to this number. All right. I don't know. Maybe I should have done that later. Okay. So yeah, I'm trying to think, how can I do this all at once? I guess I'm going to have to do that later. So we'll do the 20. Let's go back. We're doing this calculation now. I'm sorry. I'm really ready for this video to be over too. 21,007 times e raised to the power of, so here's my exponent button here. We're going to raise that to the power of parentheses, and now I want this number here. So now I'm going to go through that calculation again. I'm sorry to have to do that, but let's see if this will work. 11,958 divided by 21,007 equals, take the natural log of that. I don't know if that worked. I don't think that worked either. I guess this calculator is not going to let me do this in the most precise way. So I'm just going to use what I have here, but I'm afraid it might not be precise enough. So 21,007 times e raised to the power of, parentheses, I'm just going to type in what I have here. Hopefully it's going to be close enough. So negative point, no, it didn't let me do that. Negative 1.878, take the negative of that, times 5. All right. And so this looks like what the calculation should look like. 21,007 times, this is e, raised to the power of that value for r, which again, do as I say, not as I'm doing here. You want to keep more decimal places than what I have here. And then times the time, which is 5. All right, so hopefully your calculator is a little more user-friendly. You'll be able to do that. And so I hit enter and we get this amount. All right, so $8,214.12. This time we're being asked to round to the nearest hundreds place, so which is this value here. Because the tens place is a 1, I will round this down, so I'll keep it as a 2. So my final answer, rounded, as they've asked me to do, is going to be $8,200. So that's how much you would predict the value of the car to be after 5 years. Okay, one last problem. I'm sorry this video took longer than I expected, but this problem should go fairly quickly. The population, actually I have 2 more problems it looks like. Oh no, okay. The population of an animal in a national forest is modeled by the formula P equals 12,800 plus 1,000 times the natural log of t plus 1, where t is the number of years from the present. So they're giving you the formula here. Use the formula to determine how many animals are now in the forest. Well now, so again, t is the number of years from the present. Now would be 0 years from the present, right? Now would be right now, not in however many years from the present time. And so that would be at time t equals 0. And so that's what we will plug into the formula here. So for part A, we'll get P equals 12,800 plus 1,000 times the natural log of 0 plus 1. We're plugging in 0 for the time. So what's going to happen here is 0 plus 1 is going to be 1. The natural log of 1 is actually 0, right? We learned this back in like 4.2. Log base anything of 1 always equals 0. So natural log of 1 is also 0, but you could use your calculator to compute that. And so we're going to have 1,000 times 0, which is also going to be 0. And so really, when you plug in 0 for the time, this part of the formula is just going to disappear. And you're left with 12,800 plus 0, which is still just going to be 12,800. And so this number here represents the population at the present time, is what we're learning from that. All right. Part B, use the accompanying graph to estimate the number of years that it will take for the animal population to reach 16,000. So here's 16,000 right here on the y-axis, right? This is the population right here, 16,000. We're going to find the corresponding point on the graph that corresponds to the 16,000. Right, which is going to be this point right here. And then we want to look at the time that corresponds to that point, right? So this is the point for which the population is 16,000. What is the time for that point? So we look at the x-axis to find that time. And it looks like it's going to be about right here. Now notice this is going by 5s, right? This is 5, 10, 15, 20. 25 would be this line right here, and it doesn't quite get to 25. So it's between 20 and 25. So a good estimate, hopefully Math Excel is going to be a little bit flexible here, but I would say 22 or 23 years seems like a good estimate for that. All right, 22 or 23 years. So this is part B, estimating the time using the graph. It would be 22 or 23 years. I think Math Excel would accept either of those answers as correct. Part C is saying to answer the same question, but using the formula. So how long will it take for the population to reach 16,000? Using the formula, that means we want to plug in 16,000 for the population. So we're going to get 16,000 equals 12,800 plus 1,000 times the natural log of t plus 1. So I'm really tempted here to just erase part A. I took up a lot of space doing that particular problem. And the reason I don't want to is because I'm saving my notes from these videos and I don't want to erase something. I'd like to keep all of it there. But I think in this case, I'm desperate enough. I'm just going to go, and I'm ready for this video to be over. And so I can't think of a better solution. So I'm just going to go ahead and erase part A. It's recorded on the video, so it'll be saved that way. And then we'll put part C here. All right, so this will now be part C. So let's go ahead and solve this equation. So what we're going to do is we want to solve for t. It's stuck inside of a logarithm. So we want to use, but we will convert it to exponential form to get t out of the logarithm. But before we can do the loop to convert it to exponential form, we got to get all this other stuff out of the way. You have to have the logarithm by itself in order for that loop process to work to convert it to exponential form. So first I have to get rid of the 12,800. Since it's being added to this, I will subtract to cancel it out from the right-hand side. So I'll do the same thing to the left-hand side. So I'll subtract the 12,800 over here. And so we're going to end up with 3,200, if I'm not mistaken, equals 1,000 times the natural log of t plus 1. And then we will divide by 1,000, right, to get the logarithm by itself. We're dividing because this is being multiplied here, so to cancel it out, we will divide by it. So we'll divide by 1,000. And while this looks like it doesn't work out so nice, go ahead and do it in your calculator. You'll see you actually get a pretty nice result here. It's just going to be 3.2. So it's a decimal, but it's exact, and it's a good way to write the answer there. So 3.2 equals the natural log of t plus 1. So now we're ready to convert this to exponential form. We start with the base of the log, which is not actually written here. And you might say, oh, that means it's base 10, but not this one, right? Natural log is log base e, right? The base is e. And so we'll start with that base of e. I'll do that over here. Raise it to the power of whatever's on the other side of the equal sign, which is 3.2. And then set it equal to what's inside the logarithm, which is t plus 1. All right, so that's converting it to exponential form. Now t is out in the open where I can solve for it. And I will go ahead and do that by subtracting the 1 to the other side. And I'll get e to the 3.2 power minus 1 is equal to t. Now this is my, I guess either way it's going to be the exact answer, but it's still an exponential form. You don't want to type it in like that on Math Excel, so we're going to type this in our calculator to get a result. And then that result's what we'll type into Math Excel. And it probably would have, if it doesn't work out nice, it'll have some directions on how to round your answer. I don't know what they are. They're not on the screen. All right. So let's go ahead and clear that previous problem out. So we'll have e raised to the power of 3.2, right? Minus, let's see if this will work. Minus, okay, good. Minus 1. And so we get 23.5, right? Years, right? It's the number of years it would take, which is pretty close to our estimate, right? We thought 22, 23 years. It's 23.5 to be precise, right? So, and again, if I'm going one decimal place, I don't know what Math Excel is going to tell you to do, but if I'm going one decimal place, I use the 3 to determine how I round. So I'm going to round it down to 5. So 23.5 is what I'm going to put here. So 23.5 years, according to the formula. All right, one more problem to go. I guess the nice thing about having this recorded as a video is like if you feel like you got the hang of it or you understand what's going on, you can skip some examples. This is another logarithmic one. I want to do this one though because This is the one that tends to show up on the test. So I like to do this one in class so that you see it in class, you see it on the homework, and then when you see it on the test, hopefully you'll know what to do with it. The sound level L in decibels is given by the formula L equals 10 times log base 10, right? This one's log, so that base is a 10 since it's not written there. And this one's a little confusing. This is an I. I times 10 to the 12th power decibels. Now, sometimes students will confuse this as being part of the formula. They put a space there on purpose, and they also made sure to refer to it over here. That's the units of L. That's not actually part of the formula. So you really should just kind of disregard that. This is your formula right here. Right? L equals 10 times log base 10 of I times 10 to the 12th power. A lot of 10s going on there. Where I is the intensity of the sound in watts per square meter. The sound level is 90 decibels, right? So you have two variables in this problem. You have L and you have I. You have to decide where to plug that 90 in, and I get a lot of students that make the wrong choice. It's sound level, right? Sound level is L. It tells you in the problem, it describes it multiple times where that number should get plugged in. That's going to get plugged in for L, right? L is equal to 90. And, whoops, I don't know why I'm putting an equal sign there, times log base 10 of I times 10 to the 12th power. All right. And they want us to find I, right? And that should also give it away. What value of I gives you the sound level of 90 decibels? So they're asking you to find I, they're giving you L, right? That means this must be L if they're asking you to find I. So this is the equation we want to solve. We want to solve it for I. Just like in the previous problem, we can't convert this to exponential form until the logarithm's by itself, which means this 10 has to go first. It's being multiplied to the logarithm, so to get rid of it, we will divide by it. We'll divide by 10 on both sides, and we'll get 9 equals log base 10 of I times 10 to the 12th power. Now we can do the loop to convert this to logarithmic form. We start with the base of the log, which is 10. That'll be the base of my exponent. Raise it to the power of whatever's over here, which is 9. Set it equal to what's inside the logarithm, which is I times 10 to the 12th. Again, that's scientific notation, right? The times 10 to the 12th is how we write scientific notation, but it also is literally a multiplication. So to solve this for I, to get rid of the 10 to the 12th, you divide by it, right? To cancel out the multiplication. And so you get this. Which you can plug into your calculator, right? That's going to solve it for I. So we'll have I equals, but you could also just simplify this as an exponent. The base will stay the same. So the 10s don't cancel each other out. The base stays the same, and you subtract the exponents. 9 minus 12 gives me -3. And I see students write this answer on their test. So I have to assume that's also acceptable on your homework on Math Excel. And so you can just write it in this form, but you could also write it like this. I'd accept this as well. If you plug it into your calculator, you get this as your answer, 0.001. Right? And so that would be okay as well. Now for Math Excel, I don't know if they're also okay, if they're going to be that flexible or not. So again, click on View an Example to see how they format their answer, and that's how you should format the answer when you're typing it in on the homework. All right, this video has gone on long enough. That concludes the lecture on section 4.4, and that concludes chapter 4. So once you get through this homework, start working on the practice exam, get ready for the test. If you're one of my students, please contact me if you have any questions or concerns.